This video disc self-instruction course is about power flow in the ATX Automatic Transaxle. When you have completed this course, you should be able to 1. Identify the unique design and operating features of the ATX Transaxle. 2. Explain how power flows into and out of the torque converter. 3. Identify the power flow components in the torque converter, planetary gear train, and final drives, and explain each component's function in power flow. 4. You should be able to describe the gear progression in each forward position of the shift selector. 5. Identify each of the clutches and bands that control the planetary gear train operation and explain the function of each. 6. Name the clutches and band applied in each gear. And 7. Trace power flow through the transaxle in each gear. In escort and lynx cars with automatic transmission, the ATX Automatic Transaxle is the heart of the front-wheel drive. The transaxle is bolted to the engine and is driven by the engine crankshaft and flywheel. Its output is through a final drive and differential to the front axle half shafts. We will describe the ATX in 3 general sections. 1. The torque converter. 2. The planetary gear train. And 3. The final drive, which drives the differential. The ATX resembles other Ford 3-speed automatics in many ways, but there are important differences. First, in the torque converter, we have a splitter planetary gear set, which is installed between the converter cover and the turbine. It consists of a sun gear, a planetary carrier, and a ring gear. This gear set allows the main gear train to have a split torque input of hydraulic drive from the turbine and mechanical drive from the converter cover. Second, the main gear train thus has 2 input shafts, a turbine shaft for all hydraulic input, and a smaller diameter intermediate shaft for split torque input from the splitter gear set. Third, to drive the oil pump, which is located at the opposite end of the gear train, a third shaft is used. This is the oil pump drive shaft, and it turns inside the intermediate shaft. The main planetary gear set is a compound design similar to the FMX and the automatic overdrive. But here's the 4th difference. Its output is always through these splines to the final drive input gear. And 5th, the friction clutches and band functions are different because of the gear train arrangement. In the automatic transaxle, gear selection in P, R, N, D, and 1 is the same as other Ford 3-speed automatics. In D range, the transaxle starts in 1st gear and upshifts progressively to 2nd and 3rd. 3rd being high or direct drive. Downshifts are 3rd to 2nd and then 2nd to 1st. 1st gear is freewheeling in D range. In range 2, there is no 2nd gear start as in other Ford 3-speed automatics. The ATX starts in 1st gear and then upshifts to 2nd gear. 3rd gear is locked out by the hydraulic system. If the selector is moved manually from D to 2 at normal road speed, the transaxle will downshift to 2nd gear. As you coast down to a lower speed, it will automatically downshift to 1st gear. In range 2, 1st gear is freewheeling, the same as it is in D range. If the car is stopped and the selector is placed in range 1 or manual low, the transaxle starts in low gear and stays there. Manual low gear has a clutch applied for engine braking. If the car is moving at road speed, and then the selector is moved from D to manual low, the transaxle will downshift to second, then, at a lower speed, to manual low. We'll begin the study of power flow at the torque converter, which acts as a fluid clutch and couples the engine to the gear train. Here are the parts in the order they are assembled: the impeller, the reactor, and the turbine all work just like in other converters you are familiar with. The new parts are the splitter planetary unit, composed of a sun gear that splines into the turbine hub, planet carrier assembly that drives the intermediate input shaft, and planetary ring gear that is splined into the damper in the converter cover. The damper, similar to the damper in the automatic overdrive converter, cushions the mechanical input drive. Let's put the parts together as they are involved in power flow. For mechanical input, we start at the damper in the converter cover. The splitter planetary ring gear slips into the damper splines, so the ring gear will always turn with the converter cover at engine speed. Now the planet carrier assembly fits inside the ring gear so that the pinion gears mesh in the ring gear. And now the intermediate input shaft is splined into the planet carrier so that it always turns at the same speed as the carrier. Thus, the power flow for mechanical input is always from the engine to the converter cover, to the damper, to the splitter ring gear, to the planet pinions, to the pinion carrier, and through the intermediate shaft to the main gear train. Hydraulic input can happen two ways: all hydraulic or in split torque, hydraulic and mechanical. This is because the sun gear for the splitter planetary unit is splined into the hub of the turbine, and the turbine shaft is splined into the sun gear. With the turbine and shaft in place, we can see what happens in 100% hydraulic input. Power is transmitted hydraulically from the impeller to the turbine, and then from the turbine to the sun gear, to the turbine shaft, and into the main gear train. This is 100% hydraulic input, and it happens in first gear and in reverse. In second and third gear, we have a split torque operation. Now, the hydraulic input goes the other way, from the turbine to the sun gear, to the planet pinions, to the pinion carrier, to the intermediate shaft, and into the main gear train. At the same time, the mechanical input is through the cover, damper, ring gear, pinions, planet carrier, and intermediate shaft, as we saw earlier. The splitter planetary unit combines the mechanical and hydraulic into a single split torque input through the intermediate shaft. This chart shows the input drive percentages in each gear. First and reverse, as already mentioned, are 100% hydraulic drive through the turbine shaft, no mechanical input. In second gear, the input torque is about 62% hydraulic and 38% mechanical. The two inputs are combined in the splitter planetary unit, and the combined 100% input is through the intermediate shaft. And in high gear, hydraulic input is only 7%, while mechanical is 93%. Again, 100% of the power input to the gear train is through the intermediate shaft. Now we will look at the main planetary gear train parts, which are the low reverse sun gear, the ring gear, the planet carrier assembly with two sets of pinions, 3 long pinions and 3 short pinions. Notice that each long pinion meshes with the short pinion and the forward sun gear. There are 2 ways to get power into this gear train. First, through the turbine shaft to the low reverse sun gear. This sun gear meshes with the short pinions in the carrier assembly. As the turbine shaft drives the sun gear, the short pinions turn the long pinions. The other input is through the intermediate shaft and clutch to the ring gear. The ring gear meshes with the long planet pinions in the carrier assembly. Turning the shaft and ring gear causes the long pinions to be driven. The other sun gear, the forward sun gear, also meshes with the long pinions, but this sun gear is not shaft driven. It is mounted in a brake drum, which we have cut away. When a band is applied to the drum, the forward sun gear is held stationary, and the long pinions are forced to walk around it, as Joe is demonstrating now. The output of this gear train is always through the planet carrier. The final drive input gear is splined to the carrier. Whenever the carrier is turning, the final drive input gear turns with it. The first clutch we will look at for controlling the gear train is the overrunning or one-way clutch. It consists of an outer race, a roller assembly, and an inner race. The outer race of the one-way clutch is part of the low reverse sun gear assembly and will drive the sun gear when the clutch locks up. The clutch inner race is part of the turbine shaft assembly. Thus, the inner race will always be turning at the same speed as the torque converter turbine. For demonstration, we have removed the direct clutch cylinder from another turbine shaft, so we can see the one-way clutch in detail. Now, Joe is putting the clutch pieces together so that the roller assembly is positioned inside of the outer race. Watch the action. Driving the turbine shaft causes the clutch to lock up, and this turns the low reverse sun gear at turbine speed. If the sun gear overruns the turbine shaft, the clutch freewheels. As we'll see presently, this is how we get a freewheeling low gear. This then is a unique feature of the ATX, a one-way clutch with both races rotating instead of one race mounted stationary. The direct clutch is used to bypass the freewheeling feature of the one-way clutch. The plates are installed in a rotating cylinder which is integral with the turbine shaft and the one-way clutch inner race. And the sun gear outer race assembly has external splines that mate with the internally splined friction clutch plates. You can see that the direct clutch completely surrounds the one-way clutch. Now, if the direct clutch is applied, there is no freewheeling. The turbine shaft continues to drive the low reverse sun gear, but the sun gear cannot overrun the turbine shaft. The direct clutch locks the shaft and sun gear together, and this gives us engine braking in manual low or reverse gear. There is one more rotating clutch in the ATX transaxle, the intermediate clutch. The intermediate clutch cylinder is splined onto the end of the intermediate shaft. This clutch will always be driven at the same speed as the intermediate shaft. Now watch as Joe again installs the planetary ring gear into the clutch plate splines. This clutch is applied in second gear and in third gear, and when it's applied, the intermediate shaft drives the ring gear. Thus, in both second gear and third gear, there is power flow in through the intermediate shaft and the ring gear to the long pinions in the planet carrier assembly. Let's review that. In second and high gear, the intermediate shaft drives the intermediate clutch, which drives the ring gear, and power is applied through the long pinions to the pinion carrier. Next, let's look at the reverse clutch. The reverse clutch has its steel plates and piston installed stationary in the case. The friction plates with internal splines fit over the splines on the ring gear, right next to the intermediate clutch plates. When the reverse clutch is applied, in reverse gear only, the ring gear is held stationary. With power in through the turbine shaft, the long planet pinions are forced to walk around inside the ring gear. The last holding member for the gear train is the low and intermediate band. The band also is mounted stationary in the case. around the drum, which is part of the forward sun gear assembly. And so when the band is applied in first and second gear, the forward sun gear is held stationary. With the sun gear held stationary, the long pinions are forced to walk around the sun gear. From the main planet pinion carrier of the transaxle, power is transmitted through 3 final drive gears to the differential. These 3 gears are called the input gear, the idler gear, and the output gear. They are always in mesh as shown, and are always driven when the transaxle is in gear. The input gear, as mentioned earlier, is splined to the planet carrier and always turns with the carrier. The idler gear is supported on a shaft between 2 tapered roller bearings so that it meshes with the input gear. Its only purpose is to reverse the direction of power flow. The output gear is attached to the case of the differential, which also is supported in the transaxle by 2 tapered roller bearings. The differential works just like a rear axle differential, except it is part of the transaxle and it drives the front axle shafts. Now follow these marks on the input and output gears as we demonstrate the final drive gear ratio, which corresponds to the rear axle ratio on rear drive cars. Count the turns of the input gear. 1, 2, 3, and 1/3 to 1 revolution of the final drive output gear. The final drive has a 3.3 to 1 ratio. We have now identified all the transaxle components involved in power flow and explained what each component does. Now we will describe the power flow from engine to axle shaft in each transaxle gear. For the demonstrations, we'll use this cutaway model of the transaxle, this graphic representation of the gear train parts, and this chart that shows the clutch and band application for each gear. First, let's look at the objectives for Lesson 9. To demonstrate the power flow in park or neutral, we'll start at the top of the chart. In neutral or park, the intermediate clutch is off, so there is no power flow into the gear train through the intermediate shaft. However, the turbine shaft is turning, the one-way clutch is holding, and the low reverse sun gear is being driven. As a result, the short pinions, long pinions, forward sun gear, and ring gear are all turning, but since the pinion carrier and the final drive are not rotating, no power is being transmitted. We have power in, but no power out. Next, let's look at reverse gear. In reverse gear, we have the direct clutch applied, also the reverse clutch, and the one-way clutch, so long as the turbine is driving the sun gear. Graphically, reverse gear looks like this. Input is hydraulic through the turbine shaft. The one-way clutch is locked up so the turbine shaft can drive the low reverse sun gear. The direct clutch is on to prevent the one-way clutch from freewheeling in a coast down. The reverse clutch is applied to hold the ring gear stationary, and a reverse reduction takes place in the planetary gears as the long pinions are forced to walk around inside the ring gear. Power flow in reverse is hydraulic drive from the impeller to the turbine, to the splitter sun gear, to the turbine shaft, to the one-way clutch and the low reverse sun gear, to the short planet pinions, to the long planet pinions, to the pinion carrier, to the final drive gears which turn in reverse reduction. Now, Joe has set up the cutaway for reverse gear. The direct clutch is applied. The ring gear is held stationary by the reverse clutch, so he'll hold it as he turns the turbine and turbine shaft. Watch the action. The turbine, splitter sun gear, and turbine shaft are all turning clockwise, but the planet carrier and final drive input gear are turning counterclockwise. Watch the marks and the gear reduction of 2 to 1. 1 turn of the turbine, and almost 2 turns of the turbine to 1 turn of the final drive input gear. Next on the chart is first gear, freewheeling. This, remember, is the first gear operation in D range or 2 range. The low and intermediate band is applied, and the one-way clutch locks up in the driving condition. Here is how first gear looks graphically. Power in is through the turbine shaft, hydraulic only. The one-way clutch is permitting the turbine to drive the low reverse sun gear. The band is holding the forward sun gear stationary. And a double reduction takes place in the planetary gears as the long pinions are forced to walk around the forward sun gear. First gear power flow is the same as reverse, except for the direction of gear rotation. Hydraulic drive is provided from the impeller to the turbine, to the splitter sun gear, to the turbine shaft, through the one-way clutch to the low reverse sun gear, to the short pinions, from the short pinions to the long pinions, to the planet carrier, and to the final drive gears, which transmits power to the differential. Again, let's see it on the hardware. This time, Joe is tightening the band around the forward sun gear drum, and he will again drive the turbine shaft. Now, as you can see, the planet carrier and final drive input gear are turning the same direction as the input shaft, but at a reduced speed. In first gear, the ratio is 2.8 to 1. Count the turns of the turbine. 1 turn, 2 turns, almost 3 turns. The gear ratio of 2.8 to 1 can be increased to as much as 5.6 to 1 with torque converter at full stall. Remember now that what we've seen is freewheeling first gear. The one-way clutch holds when power is applied, but freewheels in the coast condition. For engine braking, as with reverse, we need the direct clutch. Let's look at engine braking. Joe has again locked up the direct clutch. With the direct clutch applied, the turbine shaft is locked to the sun gear, and there is no freewheeling either way. The direct clutch is applied for first gear only in the manual low range 1. To begin our study of second gear power flow, let's go back to our clutch and band application chart. In second gear, the low and intermediate band stays applied, and the intermediate clutch is applied. On the graphic, we can see what happens on the 1-2 upshift. The band stays on, so that the forward sun gear is still held stationary. The intermediate clutch comes on, so that the input drive from the torque converter is now through the intermediate shaft to the ring gear. Remember now that this is split torque input, 62% hydraulic, 38% mechanical. There is a single reverse reduction in the gear train as the long pinions walk around the sun gear. Second gear power flow is hydraulic from the turbine to the splitter sun gear, and mechanical from the converter cover are combined in the splitter planetary unit. From the splitter planet carrier, 100% of the power flows to the intermediate shaft, through the intermediate clutch to the ring gear, to the long pinions which again walk around the sun gear, to the pinion carrier, and to the final drive gears. Now on the hardware, Joe is tightening the band around the drum and has locked up the intermediate clutch. As he turns the intermediate shaft with the splitter planet carrier, the gear train output is in the same direction, but at a reduced speed. The second gear ratio is 1.6 to 1. Again, watch as Joe lines up the marks on the splitter carrier and the final drive input gear. Now the ratio. 1 turn of the input, 1.5 turns, just over 1.5 turns. Direct drive, or third gear, is our final exercise in ATX transaxle power flow. The chart shows that the direct clutch and the intermediate clutch are applied in third gear. Graphically, high gear looks like this. There is a split torque input through the intermediate shaft and clutch to the main ring gear. With the direct clutch on, the low reverse sun gear is locked to the turbine shaft and thus to the converter. This causes the main gear train to effectively lock up since two members are locked together through the converter. The planetary unit thus turns, in effect, at the same speed as the input shaft. High gear power flow is from the converter turbine and cover to the splitter planetary unit, then to intermediate shaft, intermediate clutch, ring gear, main planetary unit, and final drive. Watch as Joe demonstrates. He has locked up the direct clutch and the intermediate clutch and is turning the intermediate shaft with the turbine. This simulates a coupling condition in the torque converter, which is what causes the main gear train to lock up. One turn of the input shaft equals one turn of the final drive input. The gear train is locked up in high gear.